Alright, this is the Notes for Geometry section 1, 3 other types of geometry. And what we want to do in this section is we want to look at two types of geometry, discrete geometry and graph theory, which are both geometries that are what we would call non-Euclidean geometries. Now, in order for us to do that, let's take a moment and go back and let's first of all look at what geometry is. So when we talk about geometry, we know what we're talking about. And then second, I'd also like to look at what we've already kind of learned about points. So as I look at my description of geometry, we find that geometry is the definition is the mathematics of properties, measurement, and relationships, and this is key, of points and lines. Okay? Not only points and lines, but also angles, surfaces, and solids. But the reason why I highlighted points and lines is because when we define geometry, we're going to define them by the way we define a point and the way that we define a line. Well, so far in this course, we've looked at how we define a point as an exact location. We also have defined a point as an ordered pair. Now, both of these descriptions fall under the category of Euclidean geometry, which is primarily what we're going to study in this course. What we want to do today is look at, well, what if we change how we define a point and change also how we define a line, and see how that's going to change how we can look at a particular geometry. So that's where we want to go with things as we look at this section 1-3 today. So the first geometry we want to look at is what we call discrete geometry. And in discrete geometry, we are going to define a point as a dot. Okay? It's not an exact location, it's not an ordered pair, it's a dot. And when we talk about a line, we're going to say it's a set of dots in a row. Okay? Now, when we talk about discrete geometry, it's much less descriptive, really, than the Euclidean geometries that we've kind of already started to look at a description of a point from. So what that does is it changes our geometry. Okay? So if I look at this example right here, this is an example in Euclidean geometry of two lines intersecting. You'll notice that they intersect at one point, in this case point A. However, these two lines are two lines in discrete geometry, and you'll notice that when they intersect, in this case they do intersect with one point that they share. However, with discrete geometry, lines are not dense. There's space between the points within a line, whereas in Euclidean geometry, they are dense. Okay? So what I'd like you to do, if you can do this real quickly in your notebook, see if you can draw an example of two discrete lines crossing in which two lines do not share a common point. And then why don't you pause the video and then put it back on, and I'll show you an example of what that would look like. To introduce the next non-Euclidean geometry, I want to use the Königsberg bridge problem. And that was introduced to you in the book, and it talks about the town of Königsberg, where on Sundays it was a famous pastime to walk the bridges of Königsberg, and there were 7 of them. So this problem was famously solved by Leonhard Euler, and what Euler did is he took the land and made those points, and he took the bridges and made those lines, or in this case we call them arcs. In doing this, he was able to create what we now call a network. Okay? And a network consists of nodes, which are points in graph theory, and arcs, which are lines in graph theory. And I have the description right here of points and lines for graph theory. And you'll notice that a point is a node, and that a line is an arc. And the key to the arc is that it connects two nodes or one node to itself. So we do not have points or nodes in the middle of arcs. Nodes will always be endpoints. Well, what Euler was able to do by doing this, he was able to reframe this question to really ask, is the network traversable? And what we mean by traversable, what we mean about traversable is a network in which all the arcs may be traced exactly once without picking up the tracing instrument. So in other words, can you start in one point, go through all the arcs, and never go over an arc more than once? Okay? That is what we mean by traversable. And he was able to kind of come up with a theory that would help determine whether or not a network was traversable. One of the takeaways that I want you to have here, though, is from graph theory, once again, we have a description of a point and a description of a line. And by doing that, we're redefining this geometry. So we'll get to this example 1 problem here in a little bit, but before we do that, let's talk a little bit about how Euler came up with a solution to this problem. What he did is he looked at whether a node was what we call an even node or an odd node. And the way he determined that was the number of arcs that come into that node. So we would say a node is an even node if the number of arcs at a node is even. And we would say a node is an odd node if the number of arcs at a node is an odd number of arcs. Now, by doing this, Euler was able to come up with a reasoning for being able to determine if a network was traversable or not traversable. Okay? So when a path goes through a node, it uses 2 arcs, one to the node and one away from it. When a network has an odd node, it must be starting or finishing point for a traversable network. When a network has more than 2 odd nodes, it is not traversable. So really this statement right here is very important. Knowing that, hey, if there are more than 2 odd nodes, we immediately know that network is not traversable. Now, keeping that in mind, see if you, before you come to class next time, see if you can explain why networks 1 and 2 are traversable, but network 3 is not when we're looking at example 1. Okay, that concludes the notes for section 1-3.